All right, let's get started, everybody. So we are combining chapters 8 and 9 together. 8 and 9 are all about bonding. Okay, ionic bonding, covalent bonding, mostly covalent bonding. Okay, we have actually already done the very small little portion that was on ionic. We did that the day right before break. I'm sure you remember everything about it. Okay, and the very last thing we were talking about, so what was just before this slide, we were talking about the concept of polarity. And to be more specific, what makes an individual bond polar or nonpolar? And what we're going to sort of transition to is not just is a bond polar, but is an entire molecule polar or nonpolar. So, for example, if I have this whole thing, this is a big whole molecule. If I say, is the molecule polar, what I'm really asking is, does one side of the molecule have an overall more negative charge and the other side have a more positive charge? Okay. So by the time we get to the end of chapters 8 and 9, you will be able to draw the Lewis structure for any covalent compound. You'll be able to tell me what shape it is. All right, and you'll be able to tell me, is the molecule polar or not? Okay. And in order to answer that question, you have to think about a few things here. Okay. First and foremost, guys, for an entire molecule to be polar, it must contain some polar bonds. Okay? If everything within your molecule contains non-polar bonds, then you're not going to have a polar molecule. So first of all, and this will happen most of the time, whatever molecule we're looking at has got to contain polar bonds within it. The second and biggest thing we'll have to think about is geometry. Now, what I mean by that is shape. Okay. Tetrahedral, trigonal planar, bent. Are these words familiar to you? Okay. So what I just want to show you, all right, is some shapes that can cancel out polarity. Okay, for example, all right, this is a compound that we are all exhaling right this very moment. Carbon dioxide. Forgive me for not drawing in all my lone pairs in that Lewis structure there. Carbon dioxide has a linear shape to it. Okay, now, this compound, carbon dioxide, contains polar bonds. And let's just refresh our memories, guys. We are still in a time of year when you're going to see in free response, you're going to see statements, true statements, that you have to explain why the statement is true in 2 sentences or less. Do you remember we did those on our last test? Okay. So let's say you come across a statement that says carbon dioxide contains polar bonds. It does. It's a polar bond. That's a polar bond. Carbon dioxide contains polar bonds, but as a molecule is nonpolar. And you are supposed to explain why that is. Okay? Well, remember, we're in this time where you've got to be able to explain yourself. So let me give you the AP Chem lingo here. Right? You can't just say, well, linear is a symmetrical shape. Don't use the word symmetrical. Okay? For some reason, the AP graders don't like that word. What you would say is something along the lines of, although it contains polar bonds, the linear shape, and here's the big catchphrase, the linear shape cancels out the polarity of the bonds. That's the million-dollar phrase right there. So although this molecule does contain polar bonds, it does, the linear shape cancels out the polarity of those bonds. And linear is not the only shape that can do that. Okay, it's just one of them. Here's another shape that can do that. Should be familiar to you from Chem 1. Trigonal planar is a shape that can do that as well. We've got 3 bonds here. 1, 2, 3. Each of those bonds is polar, but it's the same phrasing. Trigonal planar is a shape that can cancel out the polarity of those bonds. Here's another one that's familiar to you. Tetrahedral. Oops. Okay. There are more shapes above this, and it depends on whether you took regular versus honors in 10th grade chemistry. It depends on who your teacher was. Most of you will have learned what I call the basic shapes: bent, tetrahedral, linear, trigonal planar, trigonal pyramidal. But there are more shapes. And we are AP and we are advanced. So we will be learning some of these extended shapes. And I'm just going to show you, it's like a little sneak preview of some of them today. Here's one of the extended shapes. It's called trigonal bipyramidal. Okay, that's a shape that is symmetrical. It's a shape that can cancel out the polarity of polar bonds. That's a shape most of you probably don't know. Here's another one that's probably new to most of you. It's called square planar. Not to be confused with tetrahedral. This one is flat. It's a flat X. Here's another one, my favorite. It's called octahedral. Now, what do these shapes all have in common? These are all shapes that can cancel out polarity. Just out of curiosity, just want to see if anybody notices this. This shape contains how many total bonds? 6. Why the prefix for 8? Imagine if you put a flat plane, like a piece of paper if you want, or a piece of cardboard or something, on all 3, or connecting these 3 points. There would be 8 faces. If you made that into a shape, you'd call it an octahedron. Okay? I wouldn't test you on that. I just wondered if anybody had noticed that. Okay? So you have a handful of symmetrical shapes. You also have some shapes that will always give you a polar molecule, as opposed to these, which will typically give you a non-polar molecule. Okay. For example, this is one we're going to see a lot, because this is the shape of water. Water has a bent shape. Okay. If you ever had to explain, using AP Chem terms, why water is polar, your explanation would be very similar. You would say it contains polar bonds, and bent is a shape that does not cancel the polarity of those bonds. It's almost the same phrasing, except just put the word not in there. Bent is a shape that does not cancel out the polarity of bonds. So bent molecules, always polar, no matter what. Okay. Here's another shape that will always be polar. You should be familiar with. Trigonal pyramidal. It's like a very short tripod kind of shape. Trigonal pyramidal does not cancel out the polarity of the bonds. Okay, and there are others, but here's the point, guys. What we're going to focus on today, we're going to do one quick little topic after this, but our big focus today is going to be on reviewing how to draw Lewis structures. We're really going to get into the nitty-gritty of predicting shape, not today, but on Friday. So if you are worried, like, gosh, I don't remember these shapes, it's okay. We'll figure it out on Friday. Okay? I'm not expecting you to predict shape at this point, which is why I give you the shapes of these guys. What I am going to ask you to do here is to tell me whether these molecules as a whole are polar or not. I showed you this term last class. You may not remember it. If you ever see this, does something have an overall dipole moment? That's just a fancy way of saying, is the molecule in general, overall, polar or not? Okay. Try these. All I'm asking you to do is tell me whether these molecules are polar or not. Go. Okay, so I'm going to put up the answers, and before I do that though, I want to just tell you that on my slide that has the answers, I have drawn the Lewis structures for all of these. Now, do I expect you to remember how to do that? Yes and no. Okay. We are going to review that today. Okay, but I just want you to get used to seeing them. All right, so let's just talk these out a little bit. Okay, so in the first two that you were given, these molecules actually only contain one single bond within them. Okay, is that one bond right there, is that a polar bond, yes or no? Yeah, it is. If the whole molecule only contains one bond and that bond is polar, then the whole molecule must be polar. Now, part of what else you were asked to do is to indicate where are the electrons being pulled. Because if we say a molecule is polar, that means the electrons are being pulled to one side of that molecule. Do you remember how you decide which element is pulling the electrons more? What's that word? Which element is more electronegative? Yeah. Which corner of the periodic table has the more electronegative elements? Top right. Okay. So what do you guys think? Hydrogen versus iodine? What do you think? Which one's more electronegative? Iodine, yeah, likely, okay. Second one here, again, a molecule that only contains one bond, is this bond polar or nonpolar? Nonpolar, so this is a nonpolar molecule. Now, I didn't give you the shape for this one, but I figured you could probably guess. What is the shape of this guy? Tetrahedral? Okay. And the answer is it's nonpolar. But tell me this, it contains polar bonds. What's that phrase? It has polar bonds, but it's nonpolar because why? Thank you. The shape cancels out the polarity of those bonds. Okay? we've got, oh, well, actually, let me come back. Which element, carbon or the chlorines? Which is the more electronegative element? Chlorine. Okay. So these electrons are going to be pulled to the outside. Here's water, which I gave you the shape. Bent, a shape that does not cancel the polarity of its bonds. Which is the more electronegative element, oxygen or hydrogen? Oxygen, okay. I gave you the shape of this one. It's nonpolar, okay. Sulfur, oxygen, which one is more electronegative? Oxygen, okay. Last one, ammonia, polar. Trigonal pyramidal does not cancel out the polarity. Which element is the more electronegative element? Nitrogen, okay? All right. Now, if you are feeling a little nervous with this, like you didn't know all the answers right away, don't worry about it. We're going to come back and review it once we've really talked about shape properly. We're going to change gears here a little bit, and this is why I had you get your calculators out. We're going to talk about this portion that is the only math in these two chapters combined. And it's very easy. Okay, it's on a concept called bond energies. We've actually defined bond energy twice. This will be our third time defining it. All right. But before we even get into that and start getting into the math, let's just make sure we're clear on a few things. Okay? Single bonds, double bonds, triple bonds. And I'm going to do a little demonstration here for you. Okay? Guys, whenever you see a bond drawn like that, okay, we say, okay, that's a single bond. Well, what is that really representing? It's representing one pair of electrons that are being shared. And I need to make sure that you understand the relationship between length and strength. Here's my little demo. Okay, I want you to imagine that my hands, each hand is a carbon atom. Here's one, here's two. Okay? They're connected with a single bond. I'm going to use a rubber band. This rubber band represents one shared pair of electrons. Okay, and if you'll notice, if I just have this one rubber band, I can stretch my hands, a good distance apart. I can stretch this rubber band pretty well. And, is the rubber band tugging on my fingers? Yeah, but not a lot. Okay. Let's see if I put a second rubber band. Now I'm using this to indicate that I have two shared pairs. I can't stretch my fingers quite as far apart as I did before. And I'm feeling a stronger force pulling here. If I go to 3 rubber bands, 3 shared pairs, I definitely can't pull this as far apart. And I'm feeling a much stronger force on my fingers here. Okay? This is an inverse relationship. Single bonds are relatively long in length compared to double and triple. They are also relatively weak compared to a double or a triple bonds. Triple bonds, relatively short in length, but much stronger than the other two. Okay, just want to make sure we all remember that. And since we're talking about strength, let's put some numbers to this. The energy, okay? This is a term that is really important for you guys to know. Write it down. Bond order. It's not a word I'm going to use a lot today, but it is going to come in handy later on down the road. In AP Chem, because we're very fancy, sometimes I'll call this a triple bond. Sometimes I'll say that this has a bond order of 3. It's just a fancy way of saying the same thing. I could say this is a double bond, or I could say it has a bond order of 2. This has a bond order of 1. And you might think that's, why would I ever use that term? It's going to come in handy, not today, but later on, I promise you. Okay. So let's get to the math here. One more time, let's define bond energy. Energy required to break a bond. Ladies and gentlemen, that's an endothermic process. Let's refresh our memories. Are endothermic heats, energies, positive or negative? Positive, very good. If energy is required to break a bond, what do you think happens when you form a bond? Energy is released. Exothermic. Okay. Now this is a symbol we haven't seen in a while. I'm sure you remember what it means, right?
Yeah.
What is delta H? Change in heat? Do you remember the fancy word for heat energy? Enthalpy. Yeah. Okay. Way back, well, not so far back, maybe like October, November, when we did thermochemistry, we had multiple ways to calculate the change in heat for a reaction. Think about it. Do you guys remember when we got the textbooks out and you had to look up numbers in the chart in the back of the book? We did products minus reactants. Do you remember that? That was delta H. Do you remember Hess's law problems where you rearranged the equations? A lot of you liked those. That was calculating delta H. We had multiple ways. Here is one more. Do you remember what this symbol means mathematically? Yeah, summation. Summing up all of the bonds broken, the energies associated with all the bonds broken in a reaction, minus all the heats of the bonds formed. Okay? And just make a note to yourself, you don't have to memorize any bond energy values. I will give them to you all today on the slides, but when you get to the problem set, guys, you are going to have to use this chart. On page 316, you don't have to go to the back of the book, they're not in the appendix or anything. There's a whole chart with bond energies listed. You'll need that for your problem set. Okay, let's do an example problem together. We'll start with a simple one. It says, using the bond energies listed, I give them to you, calculate delta H for this reaction. Thing that jumps out at me, guys, I see coefficients. You may assume it is balanced. Okay. Bonds broken minus bonds formed. Now think about that for a second. Let's use a little common sense. Which side of the reaction, reactants or products, which side will I be breaking bonds? What do you think? Reactants, yeah. You're forming product. You'll be forming bonds on the product side. Okay. So delta H equals, I'm going to put a big brackets here, set of brackets. Bonds broken, reactant side. All right, here we go. First thing I'm going to break is an end-to-end triple bond. It's got a coefficient of 1. I'm just breaking one of them, and that's its bond energy, 941. It's not the only thing I'm breaking. I'm also going to be breaking some H to H single bonds. Not just one, I'm going to be breaking 3 of them. And that's it for everything that I'm breaking. bonds broken minus bonds formed. I'm going to be forming some N to H single bonds within ammonia. Now don't answer immediately. Be careful. How many N to H single bonds am I going to be forming? The answer is not 2. 6. Be careful, okay? This is what ammonia looks like. We just drew it out a moment ago, or I did. Okay. Each individual ammonia has 1, 2, 3 of those bonds. 3 times 2. So there's 6 of them. Okay. Put that all together. And you get negative 109 kilojoules. Okay, 2 questions for you. How come my answer is in kilojoules when everything given to me was in kilojoules per mole? What happened to the per mole? I multiplied times the what? Yeah, the coefficients. Multiplying times coefficients is essentially multiplying these times a number of moles. The unit moles cancels out. My second question to you is, my final answer is negative. What kind of a reaction is this? Exothermic. If that reaction were going on inside this cup and I had my hands on it, would it feel hot or cold to me? Feel hot. Okay. And that's it. Right? Now, in all honesty, guys, this was a pretty simple one. Would I give you one this easy? Probably not. Here's one that's a little more your speed. Don't you love it when I say that? I know. Yes! Yes! Get it! Okay. Yeah, I know what you're thinking. What's going on here? I mean, there's like an equal sign in the middle of things. What is happening? Okay, it's not actually an equal sign. Okay, first of all, I'm going to get you started, but keep it simple. Bonds broken minus bonds formed. Here are my reactants. I'm sorry I couldn't fit it all in one line. Reactants, products. Okay? I'm going to help you with this guy. All right? This is an organic compound, and this is how organic compounds are sometimes written out. Just for the moment, I want you to ignore this number 2. It's just a coefficient, but just ignore it for a moment. I'm going to draw this guy out so that you can see what it looks like. Okay? Get a better marker. Let's see. Hold on. Okay, so what I want you to do is kind of move your eyes back and forth from the slide here to how I draw it on the board and see if you can kind of follow what I'm doing. I'm moving my eyes from left to right. Here we go. Ready? I'm starting with that first carbon. And it has 2 hydrogens joined to it. That's not an equal sign, that's a double bond. Double bond. To 1 carbon that has 1 hydrogen joined to it, which is now joined to a final carbon that has 3 hydrogens attached. That's what that guy looks like. If you are concerned with how was I supposed to know that, you will get more comfortable with this as we review Lewis structures. Okay? But let me just say something real quick. What if you had no idea? Let's say you just looked from left to right and you did this. C to H to H double bond to C to H to C, blah, 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 blah. See what you remember. This is illegal. You can't do this. Does anybody remember something specific about hydrogen specifically? Why can't I do that? Right. Hydrogen can only have 2 electrons next to it. Hydrogen can only support 1 pair of electrons. Hydrogen can only be joined to 1 thing. You could try all kinds of combinations. This is the only way this would work. Okay, so I drew this one for you. You'll notice the first product is almost the same compound. It just has a different ending. I think you can handle it. Let me help you get started, and then you're on your own. Here we go. Ready? Bonds broken minus bonds formed. Okay, bonds broken. How about we count how many C to H single bonds are going to be broken first? Ready? Let's count. 1, 2, 3, 4, 5, 6 times 2. So 12 total C to H bonds. That's the first thing to be tallied up. Take your time. Be organized. Try this. You can do it. Yep, I'll go back. The 2 go, each coefficient goes for the entire molecule after it.
Yeah.
So, guys, would you guys agree that, the math is not difficult, but would you agree that it is easy to make a small error? It is. That's why I said take your time, try to stay organized. What I mean by stay organized is, for me, it's very helpful to kind of keep track of which bonds I have tallied up and which ones I haven't yet. Okay? I will tell you that on our next test, you're going to have a question very similar to this. Okay? If you are still feeling a little nervous on, I wasn't sure how to draw this out, you will feel more comfortable, especially after today when we review Lewis structures. Okay? But when you see a question like this, just slow down, take your time, stay organized, and as always, if you're really good about showing your work, and I can see that the reason your answer is different from mine is because you have the number 6 here instead of 12. If I can see that, minus a half a point instead of 10. All right? But believe it or not, that is it for the math. That's it. That is the only bit of math in this chapter 8 and 9 together. So let's move on, guys, to kind of the main event for today, which is reviewing Lewis structures. So by the end of chapter 9, ladies and gentlemen, I should be able to give you any covalent compound I can think of, and you will be able to give me what I consider a complete description of that compound. Now, what does that include? That includes being able to draw it, the Lewis structure. This is what we're going to focus on today. That includes telling me its geometry, its shape, its bond angle. We're going to talk about this on Friday. Something else that's in chapter 9 is a concept called hybridization. I don't think anybody does that in Chem 1. Maybe you do. Okay? But if you can tell me all of these things about a compound, you are giving me what's called the localized electron model, a complete description of that compound. So we're going to focus here today. And guys, the gist of a Lewis structure, there's a couple of things you need to bear in mind. The first thing is that electrons in a compound are not locked in place. Okay? Within a compound, electrons can move wherever they are needed. Just because fluorine has 7 valence electrons doesn't mean those 7 have to be around fluorine. They can move wherever they are needed. Now, what determines where they're needed? We draw Lewis structures based on the assumption that most elements we're going to deal with want 8 electrons around them. What's so special about having 8 electrons? Why do all the elements want that? Why do they want to be like the noble gases? It's stable. It's very energetically stable. It's like the elements are in their happy place. Okay, don't write that on a test, please. Okay. But the point is, electrons will shift around however they are needed to in order for these elements to get 8 electrons around them. And let's be even a little bit more specific. I'm going to talk less and less about how many individual electrons are around an element. I'll talk more about how many pairs are around an element. 8 electrons is how many pairs, ladies and gentlemen? 4. Most elements will have 4 pairs. There are some exceptions. We just talked about one a moment ago. How many pairs will hydrogen have next to it? 1 pair. You may or may not have seen these in Chem 1. Beryllium will only accommodate 2 pairs next to it. Boron will have 3. It's not that these 2 elements couldn't support 4 pairs. They can. They just don't. Okay. Beryllium will have 2. Boron will support 3. 3 pairs. But every other element we come in contact with is going to have 4 pairs around it. It's going to obey that octet rule. So what I'm going to do, guys, is I'm just going to do some examples with you to kind of model the thought process. There are a variety of ways to teach drawing Lewis structures. Different teachers teach it differently. I'm not saying my way is the best way, but the method that I'm going to show you, the beauty of it is that it works for very simple compounds, but it also works for some of the more complex ones. So I'm not saying it's the best, but pretty much is. No big deal. All right. For those of you that have the PowerPoint slides, this slide and the next just have these steps for how to draw it. So you'll notice that I am going through these steps. Let's do a few examples. Let's say I were to give you this compound. Phosphorus triiodide. First thing you want to do is decide which element is going to be your central element. Go with your gut instinct. What do you think? Phosphorus, you're right. It's usually the one written first. Not always, but usually. It's usually the one that there is only one of. Okay? Please make a note to yourself, ladies and gentlemen, if you're given a compound that has carbon in it, carbon, always central. Always write it down. Okay? If you see carbon, carbon is automatically your central. Okay, let's tally up electrons. Let's see how many electrons we're dealing with here. Use your periodic table. Please tell me, phosphorus has how many valence electrons? You're asking Siri. Come on. How many? 5. Thank you. How many valence electrons does iodine have? 7, and there are 3 of them, so that's 21 plus 5, that's 26 total electrons. But as I said, guys, I care less about how many electrons there are. I care more about how many pairs. 26 shoes is how many pairs of shoes. Thank you. Okay. The next step says to draw a framework. Well, we said that we would put phosphorus in the center. And we'll draw these iodines around. If this is my central atom, do you know what you call these ones on the outside? You know the word? Terminal. These are my terminal elements. Like you're at the airport. You know, you come into the airport and then you go out to the terminal to catch your plane. Okay. So we've drawn a framework using single bonds. Now let's just stop for a second. What does this line actually represent? 2 electrons, 1 pair. Simply drawing this, I've used up 3 of my pairs. I had 13. I have 10 left. If, ladies and gentlemen, you have pairs left over, which you won't always, do you know what these are? These are shared pairs. If you have leftovers, there's something else. Remember? Lone pairs or unshared pairs, your choice. Do you remember how these are drawn? Not lines, dots. Do you remember where you should put them first? It matters. Not the central. What are these called? Terminal. Okay, so watch. Here we go. I'm going to draw them as dots. I have 10 pairs to work with. Here we go. 1 pair, 2 pair, 3 pair. Can I put any more on this guy? Why not? He has 8. He has 4 pairs. He's full. Okay? 1 pair, 2 pair, 3 pair, 4 pair, 5 pair, 6 pair, 7, 8, 9. Where should I put that 10th? Okay? And I'm out. I've used them all up. Now I'm going to ask you what seems like kind of a silly question. Are all the elements happy? What do I mean by that? Are they happy? Yeah, do they all have an octet? Do they have 4 pairs? Do they? Yeah. Everybody's happy? That's a complete drawing. Done. And we'll talk about in a minute, what if somebody's not happy? What do you do? Let's talk about drawing these lone pairs. I was very deliberate in drawing out my dots. And guys, you have to be. You are being graded on your next test, on the AP exam, on what your drawings look like. Be deliberate with your dots. Here's what I can't stand. Okay? You're using pencil on free response, let's say. Okay? And you've drawn this beautiful structure, P, I, and this is what I get for lone pairs. It makes me nuts. Wait, what is that? I don't know what that is. Like, are those lone pairs, or did you like drop your pencil or have a seizure? I mean, I don't know what that is. If I can't tell if it's like a stray mark or a dot, I'm not going to play detective with your lone pairs. Be deliberate. Dot, dot, dot. Okay? And I don't know if anybody in here has ever seen this, but just on the off chance that someone has been told that it's okay to do this, in some chemistry textbooks and some teachers will say it's okay to draw your lone pairs like this. Are you ready? Like just lines like that. Do not do that. Dots. Make them obvious. Okay? Does that answer your question? Okay, good. All right. Let's do another example. Let's do this one. This is a quick one. What's the name of that polyatomic ion? What was the ending? Ah, thank you, ammonium. Okay. What's my central atom? Could it be hydrogen? No, it couldn't. Okay. Let's tally up total electrons. Nitrogen has how many valence? Dude, come on. How many?
5.
Thank you, 5. And each hydrogen has just 1. But what? But what? That's an odd number. That's a problem. You can't make pairs with an odd number. Okay. A +1 charge means what happened? We lost an electron. So you're going to subtract 1. Now, what if the charge wasn't +1? What if it was +3? Subtract 3. What if the charge was -5? Add 5. Okay, good. Just checking. Okay, 8 electrons, that's 4 pairs. This is a quick one. Let's draw our framework. And I'm out. Is everybody happy in this picture? Yep. Complete drawing done? Thank you. When you're dealing with a polyatomic ion, something with an overall charge, put brackets around your entire drawing and put the charge just outside. Let's do one more. Is this coming back to you? Okay. Let's do this compound. Which polyatomic ion is that? What? Nitrate. Okay. Central atom, please. What's it going to be? You got it? Let's add up our total electrons. We just saw nitrogen has 5. Each oxygen has... Okay. How do I deal with that overall charge? All right, let's add 1 more electron. So that's 24 total, 12 pairs. Okay. And guys, I always get asked this a lot. Does it matter the shape that you draw these? Like, would it be okay to put this oxygen on the top? Absolutely. The shape in which you draw them doesn't matter. I had 12 pairs to work with. I've just used up 3 of them. So I have 9 left. What are these again? Lone pairs. Where do I put them first? Terminal. Okay. 1 pair, 2 pair, 3 pair, 4 pair, 5 pair, 6 pair, 7, 8, 9. And I'm out. problem? Nitrogen is sad. You didn't get any cookies. Okay, well, do you remember from Chem 1? What do? I mean, you can't just add another set of dots. You don't have any more to work with. Okay, so everybody here got their cookies. He didn't, so one of these is going to be the nice person is going to say, okay, I'll share with you. Okay, it does not matter which one you choose. I'm just going to choose this oxygen. I'm going to choose this lone pair, which I'm going to erase and turn it into a shared pair. Please understand, did I take anything away from that oxygen? He still has 4 pairs around him, yeah? Is nitrogen happy now? Yes. He's smiling. Finished, complete, done? Why not? Need brackets. Okay? Do you feel like this is coming back to you now? Okay. Great, I'm so glad. Let's just get to some practice, why don't we? I know you were looking forward to it. I was too. Go get him! So, guys, I'm going to put up the drawings. You may not have gotten through all of them, and that's okay. But check the ones that you did get through at least. I'm proud that I got them all on one slide. Guys, let me say one more time. The way that you have drawn your Lewis structures doesn't actually matter. For example, my NO2 Lewis structure, I drew in an upside down L shape. You didn't have to draw it that way. You could have drawn it straight across, like I drew this one straight across. You might have drawn yours in an L shape. It doesn't matter. As long as you have the correct number of dots and lines, you're in good shape.